So let me start with an overview of what is involved in a general overview of what's involved in a control system design process, and then show what the stuff that I'm going to present, how it fits in with that. So the control design process itself is not really rigidly structured, and different people and in different industries, the process could vary from a little bit here and there, but there are some common components. Like, for example, the Is that good? Okay, so components like first gathering the requirements, modeling, design, implementation, testing, and so on. And in some segments, they actually have this V diagram, which is basically the same thing too. So they go through the requirements, they come up with what the system design should be, the software. This one comes in some, like in automotive applications, where they want to get the things faster into market, and they're doing these two things almost concurrently and so on. So what I'm going to present comes in this software design component, right? But that's what I'm going to be presenting today. So the stuff that I'm going to be presenting is about nonlinear control systems. So this is stuff that got introduced in version 10, and we've been adding stuff for control systems since version 8. We started with linear systems, and then we added capabilities for systems with delays, and then algebraic constraints, and now nonlinear systems. So what I'm going to be covering is this nonlinear systems. There's the standard nonlinear systems, not yet delays and descriptive. And the standard linear systems come out as trivial or a special case of that. So why is this important? In one word, it is applications. So you see, if you consider, you'll see many applications where the system is not linear, and there is a good number of them where the control input itself appears linearly in the system. So there has been a lot of development in terms of understanding nonlinear dynamics and control techniques to handle nonlinear systems. But one of the bottlenecks was the computation, because the computation is really heavy on symbolics. And what we hope is achieved by this functionality is it's going to ease some of that pain, and it's going to make the whole controller design process more efficient. Okay, so for the next 3 slides, I'm going to show the linearization technique to design controllers. So the first one, this is the most simple one, the Taylor linearization. So we start with either an affine or a nonlinear model. So this is the equations governing an affine model. So this U is the input variable. And that's why it's called affine, because the input is appearing linearly. And this X is the state. So this first equation is the state equation. And then we have the output equation. In Mathematica, this is how you would define an affine model. You'd specify what the A vector is, what the B matrix is, the C vector, and the D matrix. Or we could start with a nonlinear model. So in the nonlinear model, the input U need not appear linearly. So it's a completely nonlinear model in both the states and inputs. And similarly, the output equation is also completely nonlinear in both inputs and outputs. And this is the constructor for the nonlinear state space model in Mathematica. Now, to carry out the Taylor linearization, it is the same thing, just like how we would do for a regular, how we would do for a nonlinear dynamical system. We are interested in small deviations above the operating point. X0 and U0 are the operating points. We are interested in the dynamics that is close to those operating points. So once we set up these variables, we can from these equations, we can find what the governing equations for these small deviations are by doing a Taylor linear expansion. And then we neglect all the higher order terms. So these Jacobians turn out to be the A, B, C, D matrices of the linear system. And this is the state space. This is we already had since version 8. This is the state space representation. This is the constructor for a state space model. So here's the state space model. I'm linearizing a nonlinear model, and you can see the 4 Jacobians there. So the whole idea is to do controller design on this, and the challenge is how good the controller is, because it will not be good very far from the operating point. So let's look at that with look at an example of Taylor linearization in action. So I took the standard example of an inverted pendulum. So the whole idea is to keep this bob perfectly balanced. So I start with the governing equations. So the first equation is the force balance, and the second equation is the moment balance. So affine state space model, it also has a constructor where you can directly give those equations to affine state space model, and it will come up with the state space representation. So the other things are, so this is the time variable, or the temporal variable. These are my output equations. So these are the two variables that I'm interested in as my outputs. The other variables, either they are inputs or states. So any function of time it's either an input. If it's not an input, then I specify it as one of the states, and it will automatically compute what the state space representation is. So once I have this affine model, I can go ahead and compute the control. I'm using state. This is pole placement. So I want to place, so this is unstable, but say, for example, I want to place the poles at these locations. The other thing is, so usually these state feedback gains, they work for linear models. So I should actually do like this. So you see, so this is a linear technique. And it uses the linear model. But we have automated this process so you can directly give a nonlinear model, and it will come up with the gains. The only difference is, in one case, it's a matrix. This is actually the control law given as a list, because there's only one control input, there's only one element. And the reason it's like this is in case you have operating points that are non-zero, the gains will not completely capture all the information. But both these will automatically work with the next step, which is to connect the plant and the controller. So if we connect the plant and the controller together, this is the closed loop system of the unstable pendulum with that controller. And then we can simulate it. I'm starting with an initial position of 30 degrees, and I see that the controller brings it back. And see, if I go much further, it probably, see, it hangs. So it says that, this controller is not good at places far away really far away from the operating point. The other thing is, suppose I just did a linear simulation. I did not use the full nonlinear model. If I just did a linear simulation, the simulation will go through, but that is not really. So with these nonlinear models, we are able to get higher fidelity simulations and test the controllers better. And finally, you may also be interested in the control effort, how much control effort was expended in doing this. And this is the way we do it. So it's just, so this controller depended on these following states. So we just get what the state response of the closed loop system is and plug it back into the controller. The negative sign is because it's in negative feedback, and we know what the control effort is. So that was Taylor linearization. It just threw away all the higher order terms. The next level of the technique we have is called Carleman linearization. This is also kind of Taylor linearization, but it retains more information. So there are two things so we start with, I'm using a nonlinear model for the illustration purposes. This is the complete nonlinear model. There are two steps. So the first thing is we again look at deviations from the operating point, but we don't really throw away the terms corresponding to the states. We're only looking at deviations of the input. And then we just do a series expansion of the state. And all the higher order terms in the input we throw away. The second thing we do is those series polynomials that we choose as our states. And by doing that, and if you work out the algebra, it's pretty simple. So by doing that, what we end up with is a model that is linear in both the states and the inputs. There is this cross-coupling term, so it's actually a bilinear model. But we have reduced this completely nonlinear model to a bilinear model. And we hold this in the affine representation. And then the idea is to use this model to do controller design. So let's look at an example for that. Okay, this time I choose this example. So this is a therapy for the HIV infection. So I have healthy cells, that's the concentration is x1, the virus, the concentration of the virus is x2, and this is the governing equation for both the healthy cells and the virus. You see, this is the production rate, this is the decay rate, and so on. It's a pretty straightforward equation, and then this control input is the dosage level. So if I have, for example, a very low, if I have, say, a very low dosage level, I mean, then the virus is just going to go up. But suppose I have a very high value, it's going to go down, but then my healthy cells have moved out of the equilibrium position and so on. So the whole idea is, the whole problem is, how do I find what the correct dosage level is? Yeah. So the other thing from the source I got this, they don't bring the infected cells, they don't bring it all the way down to 0. They do this treatment in stages. So the target is to bring it down to 10. So I'm going to do Carleman linearization of that system. So when I do Carleman linearization, I need to say how much I want to retain. And so I say that these are the new state variables. There are multiple ways to specify this. In this case, I've used that. And what this returns is a linearizing transformation data. So in the previous example, you saw that you had to put together the plant and the controller and so on. So one of the advantages of this transformation data object is, once you have this and you design the controller in the new coordinates, you can automatically put everything together. Yeah. So from that data object, I compute what the transform system is, and I do a controller design based on that transform system. Last time I used state feedback gains. Now I'm using LQ regulator gains. I get this controller. As you can see, I can just once I have this controller, I want to compute what the closed loop system is. I'm doing a connection. So this is the automation. So we just say closed loop system with this controller, and it will give me the complete closed loop system. And I can do the simulation, and I can see that the infected cells have been brought down, and the healthy cells have reached an equilibrium value. And again, because I have that object, I just want to know what the original, okay, so because this controller was designed in the new coordinates. So the controller we are interested in is actually the controller in the original coordinates. See, so that is the original controller. You'll see it's nonlinear because I have this cross-coupling term which I specified as to start with. And then again, I substitute the state response and I get the dosage level. Okay. So yeah. So the next one, the next linearization technique. So in both these, the Taylor and the Carleman, when we linearized, we lost some information about the system. In this linearization technique, we do not lose any information about the system. All the information is stored in a transformation. So I'll start with a simple example to just show you how this works. Suppose we have this is a standard MCK system, the mass. These are all the Coriolis terms, the conservative force terms, the applied forces, but it's nonlinear because these are all functions of x. Now, if I choose the control input like these terms, and I substitute it back, in this new control variable, the system is now linear, and I can do linear controller design based on this new system and then transform it back. So this is the idea behind feedback linearization. So then the whole question is, if I have a general affine system like this, how do I find the transformation? And that's also pretty straightforward. We start by choosing the first transformation as the output and do successive differentiation. So these successive differentiations will give me the transformation. And there is an assumption that this one term should be 0. I'll say what happens if that assumption fails. So this successive differentiations is going to give me the transformation. And because it's successive differentiation, this is going to be the new dynamics. And the new dynamics are linear except for the last term, which is nonlinear in x. So then what I do is I choose that to be my new control variable. And the moment I do that, I get a completely linear system. But all the linearization information is stored in that transformation. So in block diagram, this is the summary of that. Yeah. So this, yeah, just don't worry for now about the post and the pre-compensator. That is more advanced techniques when this doesn't work. But this relationship here between the old control and the new control, that is what is captured in this feedback. And that is that feedback relation. And once we do the state transformation, we get this new system. We should get everything linear, but if that assumption fails, I said that this term should be 0. If this assumption fails, then it could happen that there are some residual dynamics left. It is not completely linear. So we are good as long as those residual dynamics are well behaved. If it's not well behaved, there are some techniques to get around it. But for this talk, I'll just assume that those dynamics either are non-existent or well behaved. So let me show an example for that, for feedback linearization. So this example is modeling the oscillations in a compressor, an axial flow compressor, and so the dynamics as such are oscillatory. So I'm going to use feedback linearization to suppress those oscillations. So I feedback linearize that system. It again returns to me this data. So this data object. So this data object has all the information about the transformation. And once I design my controller, I can put it back in the original coordinates. I can get more information about the transformation and so on. So see, once that's evaluated, I can do. So these are all the properties. We can get what the state transformation was, what was the linear system that was obtained, what was the feedback compensator. So these are this and many other information we can get. So I get the linear system and I do controller design. So this is the controller in the new coordinates. For example, if I'm interested in what the controller is in the original coordinates, I can. I'm just copying and pasting the one from above. You see, so this is the controller in the original coordinates. Although in the new coordinates we just did a linear design. And then just like before, from that same data object we can get the closed loop system and we can simulate it and see that the controller in fact works. Okay, so these were all linearization techniques. So now we have, so this is another controller that's part of the functionality, that's output tracking. So this problem is, how do we determine an output law that causes the system to follow a trajectory? We want the output of the system to follow a particular, like a robot arm or something. We want it to follow a trajectory that we specify. So this technique is also based on the linearized subsystem that we just discussed. And because it's the linearized subsystem, we should know how many states have been linearized. So the only one critical information that we have to know is the number of states, and that is given by this property, that's the vector relative orders. So we have a function for that also. So I'll explain that using this example. So this is a biological pathway. It involves the production of glucose and so on, and I want to maintain certain metabolites at certain values. So this is the governing equation for that system. And now this is the function, asymptotic output tracker. I give the system. I say what are the trajectories it should track. Okay, so here I use just constant values. In general, they could be functions of time. And then I specify the decay rates. So how do I know how many of these I should specify? That's given by the vector relative orders. So there are 6. So which basically means this system had 6 states. And the total of the vector relative orders is 6. So if I did feedback linearization, this whole system would be linearized. And that's why I give 6 decay rates. And then it's the standard way to connect and simulate. It's a state feedback thing. So we state feedback connect the system and the feedback law, and we evaluate it. And just as before, we can compute what the control effort is using the state response function. Yeah, yet another controller technique. This is output regulation. So we want to maintain the output of the system at a particular value. It could be that the system is getting excited by some disturbances that we have no control over. And in the presence of that disturbance, we want to make sure that some variables in the system are maintained at a certain level. We could also use this to model some trajectory that we want the system to follow. And then in the presence of, and we model that trajectory appropriately, and then we say that this certain variable should follow the trajectory. So the example I have here is the level control of a tank. So the flow variable is in the top tank, and I want to maintain the level of the bottom tank at a particular value. And I'm going to say that there is some disturbance over here. Some fluid is either coming in or going out, which I have no control over. And I've chosen it's going out as positive. So this could be some, so the whole thing now is, how do I model this disturbance? I'm going to assume that this is a slow system, and that I'm just, so the first two equations are this, the Bernoulli's law for the flow in the two tanks. And then the disturbance, I'm going to assume it's constant. I'm going to assume I'm going to sample, and between each sampling period that it's constant, then we'll see how good the controller fares. So once I have that, I know what the operating points are. Just like before, once I have the equations, I can use nonlinear state space model to automatically construct the state space representation. The final state is just the disturbance, which I'm assuming is 0. And the function that computes the controller is the full information output regulator. It's called full information because it's just not state feedback. It also uses the disturbance, what is the disturbance to the system, which is QD. So in this problem, I assume we can know what the disturbance is. But in case it's not, then we have to also construct an estimator for this controller. And once we have that, again, same workflow as before. We do a state feedback connect. Yeah, one thing I should know. So since version 10, we have introduced this kind of functionality, where we have this kind of typesetting where we have scaled it in case it doesn't fit. We use these glyphs to actually put so that everything is put within one page. You can browse, you can use your tooltip to see that expression, or you can click that to get the entire expression. Okay, so now I come to the disturbance. I assume that this is the disturbance. It's actually a polynomial, but I'm going to sample it at each time instant, and then I'm going to assume it's constant and see how good my controller is doing. Yeah.
What's X? The disturbance is, I'm sorry, explain the disturbance.
Oh, the disturbance is a function, that X is actually time. Yeah, so in the next variable I wanted to use X. I wanted to use time there, so I didn't want a conflict. Yeah, it's actually, yeah. Yeah, so I create this disturbance, I come up with this, I just assume that is going to be the disturbance, and then I take the closed loop system, I assume that is the disturbance, I simulate it, and I see that it in fact works. So I'm interested in the height, the second height, which remains at 3, that's what I wanted it to be, and the other one is just turned out to be 3, it's just a coincidence. So I'll just go over one analysis. So this is all the controller design techniques, and I'm just going to go over some analysis tools. So one of the analysis tools is controllability, to see if a system can go from one point to the other in the state space. So you want to know if the control effort can take it. So this is a vehicle model. It's a kinematic model. The states are the positions and the orientation of the vehicle, and this is the steer angle. And the control inputs are this is the drive velocity and the drive rate, or the steer rate. If I do a linear, if I consider okay, I have to wrap up, but I'll just get through this slide too. So if I look at the linear model, it turns out that the system is not controllable, but the nonlinear model, it's true. And there's two ways to understand that. So if you look at the simulations, this is like parallel parking your car. I mean, we parallel park our cars, and what it says is that it's only using the nonlinear model that we can see that the system is controllable. The linear model throws away too much information, and we cannot see that it is controllable. So there's two ways to do it. Yeah, okay, so let me just... So we can understand this in two ways, either using the simulations or using the computations. So using the input, we think what we do when we drive a car. We first drive and then steer, drive backward and then steer backward. And using these combinations of inputs, you'll see that the nonlinear model actually moves from point A to point B, but the linear model does not. So that nonlinear information is actually important to capture that this system is in fact controllable. And you can see that same information from a mathematical perspective, and that's using this controllability distribution. I'm just going to skip this for now, but you'll see that this is the same thing. You do combinations of drive and steer, and you can get motions like slide and wiggle and so on. And you can see that the distribution actually spans the entire controllable space. Okay, I'm just going to, yeah, so this slide, all I want to say is that it's fully integrated. All the nonlinear functions that we have added, it works just like for the linear case. So if you know how to work with the linear, it will work just like that for the nonlinear. So I'm doing state space transformation. You'll see that this syntax is just the same as the linear. Give the model, instead of giving a linear transformation, which was earlier matrix or a pair of matrices, you just give the nonlinear law. So the whole summary of this slide is it's well integrated. So to summarize the whole talk, the reason nonlinear control systems are important is because of the numerous applications. And what I hope we have done is make this process more efficient by adding this functionality, which takes away a lot of the tedious symbolic computations. And we also made sure that it's done in a clean and cohesive manner. The two main functions that I used to capture the models are affine and nonlinear state space model. The controller design techniques that we added are the exact and approximate linearization, output tracking, and output regulation. The analysis tools are many. They include controllability, observability, relative order computation, state transformation, etc. And you can find more information about these functions on the guide page and also on the marketing page.